Good morning everyone. Welcome to this session. We were looking into the solution of multidimensional parabolic partial differential equation, but which were well posed. So, in the last class we have seen how an actual problem can be maybe an ill posed problem, and how it can be converted into an well posed problem in order to have a separation of variable type of solution. Now, in the last class at the end we were starting about a three-dimensional parabolic partial differential equation and solution by separation of variable. Now, in today's class we will be finishing it over and see that how the solution will evolve using separation of variable, and then next after that we will be looking at a problem which will be a four-dimensional problem. Okay. So, let us look into a three-dimensional parabolic PDE, but which is a well posed PDE as well. Okay. So, the governing equation will be del u del t is equal to del square u del x square plus del square u del y square, subject to at t is equal to 0, we have u is equal to u naught, at x is equal to 0 and 1, u is equal to 0, at y is equal to 0 and 1, u is equal to 0. So, we have all the four boundary conditions to be homogeneous and one initial condition to be non-homogeneous, and then we will be looking for a separation of variable type of solution. Therefore, the solution will be assuming that it will be a product of three function, and each function will be a sole function of the independent variable. That means, u will be a product of a function which will be a solely function of time, another function which will be solely function of x, and then which will be another function which will be solely a function of y. So, therefore, u can be represented as x of x, y of y, and t of t. And then what we are going to do, we are substituting this solution to the governing equation, and let us see what we get. X y dt dt is equal to y t d square x dx square plus x t d square y dy square. Okay. Then we divide both sides by x y t, and we will be getting 1 over t dt dt is equal to 1 over x d square x dx square plus 1 over y d square y dy square. Now, the left hand side is function of t alone, the right hand side is function of space, it is a function of x and y. So, therefore, and they are equal, and they will be equal to some constant, and this constant has to be either 0, negative or positive, and we have seen earlier that if it is 0, then will be if it is 0 and positive, we will be getting a trivial, will be landing into a trivial solution, but we are looking for the non trivial solution. So, therefore, this equal to some constant, and that will be a negative constant minus lambda square, because we are going to formulate a standard and independent eigenvalue problem in the x direction and independent eigenvalue problem in the y direction, simply because the boundary conditions at these directions are homogeneous. So, if we have a homogeneous set of boundary conditions in a particular direction, then we will be formulating an independent standard eigenvalue problem in that direction. So, let us look into the solution of the spatial variation part. So, 1 over x d square x dx square plus 1 over y d square y dy square will be equal to minus lambda square. So, again we can write 1 over x d square x dx square, take the y varying part on the other side, minus lambda square minus 1 over y d square y dy square. Now, again this part is a function of x alone and this part is a function of y alone, and they are equal and they will be equal to some constant, and let us say this constant is minus alpha square, because if this constant is positive and 0, then we will be getting a trivial solution and we are looking for the non-trivial solution. Therefore, we can formulate the standard eigenvalue problem in the x direction as d square x dx square is equal to minus alpha square. So, we can get d square x dx square plus alpha square x is equal to 0, and the boundary condition of the original problem in the x direction should be satisfied by the x varying part of capital X. So, therefore, and since they were the differential boundary condition, we will be having a differential boundary condition here as well, that is at x is equal to 0 and 1, capital X is equal to 0. So, we can formulate a standard eigenvalue problem in the x direction because the boundary conditions are homogeneous in the direction, and we know the solution of this problem, the eigenvalues are n pi and eigenfunctions are sin n pi x. So, we write that. So, alpha n is equal to n pi, where n index n runs from 1 to up to infinity, and the eigenfunctions are sin functions sin n pi x. Okay. So, this is the solution. Now, let us look into that, let us turn back our attention to the y varying part and let us see how the y varying part looks. So, minus lambda square minus 1 over y d square y dy square is equal to minus alpha square. So, therefore, 1 over y d square y dy square is equal to minus lambda square plus alpha square, and again the combination of the two constants will be a constant, and again this constant has to be a negative constant, otherwise we will be landing up with a trivial solution which is not desirable, and we are looking for a non-trivial solution. So, let us solve the y varying part now. It becomes d square y dy square plus beta square y is equal to 0, and the boundary conditions of the original problem should be satisfied by the y varying part. So, therefore, at y is equal to 0 and 1, our capital Y will be equal to 0. So, we know again the solution of this, but in this particular case, if we see that both x varying part and y varying part, they will be constituting an independent eigenvalue problem. So, I will be writing a different subscript to indicate the solution in the x varying part and y varying part, because these two are not related at all, they are not depending on each other, and they will be formulate an independent set of eigenvalue problem. So, the boundary condition, the eigenvalues will be beta m is equal to m pi, where the index m runs from 1, 2, 3 up to infinity, and y m will be C2 sin m pi y. The index m stands for eigenvalue problem in the y direction, and n stands for the eigenvalue problem in the x direction. Now, we can look into the solution of time varying part. If you remember, the time varying part was 1 over t dt dt is equal to exponential would have been minus lambda square, and since let us look into the definition of lambda, lambda square minus lambda square is equal to plus alpha square is equal to minus beta square. So, lambda square will be nothing but alpha square plus beta square, and let us put the value of alpha and beta. Alpha is nothing but n pi, so it will be n square, beta is m pi, so it is m square pi square. So, since lambda is function of both n and m, we write lambda n m is equal to n square plus m square pi square. So, I write lambda m n here, and this will be t m n So, therefore, the solution of T m n will be nothing but another constant, let us say C3 exponential minus lambda m n square t. So, this is the solution of the time varying part, and where the constant lambda m n square is can be written as m square plus n square into pi square. Now, we are in a position to construct the complete solution by multiplying each of these components together and then adding them up by using the principle of linear superposition. If we really do that, then the solution will be constituted by summation of u m n, and there will be a double summation, because we will be considering two eigenvalue problems. One is in the x direction and one is in the y direction. They are independent to each other. So, therefore, there will be appearing two summation in the solution, indicating one summation over x over m, another over n, and another summation over y over m. So, therefore, n is equal to 1 to infinity, m is equal to 1 to infinity, and this will be 1 to infinity, n is equal to 1 to infinity, and multiplied of three constants C1, C2, C3, it will be giving you new constant Cmn and exponential minus lambda m n square t sin n pi x sin m pi y. Now, these constitute the solution of u. Now, only one step is left behind, that is the evaluation of constant Cmn, and the constant Cmn can be evaluated from the initial condition that has not been utilized till now, that is at t is equal to 0, u is equal to u naught. Now, at t is equal to 0, u is equal to u naught. So, if you write that, let us see how it comes out. U naught is equal to minus is equal to summation m is equal to 1 to infinity, n is equal to 1 to infinity Cmn sin n pi x sin m pi x sin m pi x sin m pi y. Okay. So, now we can utilize the orthogonal property of the eigenfunction. It is of eigenfunction and can evaluate this constant Cmn. So, what we are going to do next? We are going to multiply both sides by sin m pi x sin n pi y dx dy and integrate over the domain of x and y. So, u0 double integral sin m pi x sin n pi y dx dy is equal to double summation integral Cmn sin n pi x sin m pi x sin m pi y and n pi y dx dy. Now if you so this will be a double integral. So, 0 to 1, 0 to 1. So, this integral over the domain of x, that is from 0 to 1, over the domain of y, that is from 0 to 1. If instead of a constant value of u at t is equal to 0, if it would have been some function of some prescribed function of x or some prescribed function of y or some prescribed function of combined x and y, that would have been included here, and this would have been integrated by parts in that case. But since u naught is constant, in this case the left hand side, the u naught can be taken out of the integral sign. Now, if we utilize the orthogonal property of the eigenfunctions and open up the summation series, only two terms will exist, only one term will exist, that will be when m is equal to n in both the cases, because when m, we know that the eigenfunctions are orthogonal functions. So, integral of sin n pi x sin m pi x dx will be equal to 0 for m not equal to n. When they will be equal, only that term will survive. So, we will be having C m n integral sin square n pi x dx 0 to 1 multiplied by 0 to 1 sin square m pi y dy. So, we can have C m n is multiplied by this integral, as we have seen earlier, this will be equal to half, this will be again it will be half. So, it will be 1 by 2 into 1 by 2 is equal to u naught integral of sin m pi x dx 0 to 1 will be giving you value sin. So, it will be just then convert m into n sin n pi x dx 0 to 1 integral 0 to 1 sin m pi y dy. So, what I am doing, I am converting the running index x and y respectively to their original function. That means, sin the index n was associated with the in the x direction, and index m was associated in the y direction. So, I am just bringing them to that same direction, because they are basically the dummy variable. So, if we do that, then let us see how the functional variation of u naught looks like. So, u naught will be nothing but Cmn will be nothing but 4 times u naught 1 minus cosine n pi divided by n pi 1 minus cosine m pi divided by m pi, and you will be getting 4 u naught m n pi square 1 minus cos n pi 1 minus cos m pi. So, let us now construct the complete solution as u x y t is nothing but 4 u naught over pi square double summation m is equal to 1 to infinity n is equal to 1 to infinity 1 minus cosine n pi 1 minus cosine m pi divided by m into n exponential minus lambda m n square t sin n pi x sin m pi y. So, that gives the complete solution for a 3-dimensional parabolic partial differential equation. Now, I will be solving one more problem if my boundary condition is in this particular case we have considered the Dirichlet boundary condition. If one of the condition is Neumann, that means if it is the boundary at that particular location is insulated, then how it looks like. So, the next example that I will be solving is this, is that we will be solving the exactly the same problem, del u del t is equal to del square u del x square plus del square u del y square at t is equal to 0, u is equal to u naught, at x is equal to 0, del u del x is equal to 0, and at x is equal to 1, u is equal to 0, at y is equal to 0 and y is equal to 1, both u is equal to 0. So, we are having a Neumann boundary condition at x is equal to 0, and everywhere else it is a Dirichlet boundary condition, and that is homogeneous. So, now let us look into the solution of this problem. Again, we will be attempting a separation of variable type of solution. So, u is assumed to be constant of product of 3 function t of t, x of x, y of y. Now, if you substitute in the governing equation and after doing separation of variable, we will be getting 1 over t dt dt is equal to 1 over x d square x dx square plus 1 over y d square y dy square. So, again the left hand side is a function of time alone, the right hand side is a function of space alone. They will be equal, they will be equal to some constant, let us say minus lambda square, and then we will be again re-simplify the spatial varying part. So, 1 over x d square x dx square plus 1 over y d square y dy square is equal to minus lambda square. Now, since in this problem we will be having the homogeneous boundary conditions both in x direction and y direction, then we will be formulating a standard eigenvalue problem or Sturm Liouville problem in both directions independently. So, therefore, we write 1 over x d square x dx square is equal to minus lambda square minus 1 over y d square y dy square, and this will be equal to minus alpha square in order to have a non-trivial solution. So, let us formulate the standard eigenvalue problem in the x direction plus alpha square x is equal to 0. At x is equal to 0, we have dx is equal to 0, because this must be satisfying the boundary condition of the original problem. In the mother problem, we had the Neumann boundary condition prevailing at x is equal to 0. So, therefore, in the sub problem also the spatial varying part must be satisfying that boundary condition at x is equal to 0. So, at x is equal to 0, it was a Dirichlet. So, we will be having a Dirichlet boundary condition here as well. Now, we have already seen the solution of this problem earlier, that if there is a Neumann boundary condition existing prevailing at x is equal to 0 and a Dirichlet at x equal to 1, then the eigenfunctions are 2n minus 1 pi by 2, and the eigenvalues are 2n minus 1 pi by 2, and the eigenfunctions were cosine function. So, let us write that down. So, eigenvalues where alpha n is equal to 2n minus 1 pi by 2, where n is equal to running from 1 to up to infinity, and eigenfunctions x n corresponding to nth eigenvalue. So, this will be C 1 cosine, let us say alpha n x, where alpha n is basically nothing but 2n minus 1 pi by 2. So, this is a solution of the x varying part. Now, let us look into the solution of the y varying part, then we will be getting the solution of time varying part, then we will be constructing the complete solution. So, the y varying part minus lambda square minus 1 over y d square y dy square is equal to minus alpha square. So, 1 over y d square y dy square is equal to minus lambda square plus alpha square, and again this will be a new constant minus beta square in order to have a trivial solution in y direction, in order to have a non-trivial solution in the y direction as well. So, we will be constructing the standard eigenvalue problem in the y direction as d square y dy square plus beta square y will be equal to 0. At y is equal to 0 and 1, we have both Dirichlet boundary condition, because in the original problem we had the Dirichlet boundary condition in that direction, in the y direction. So, we know the solution of this problem. The solution is that the corresponding eigenvalues are m pi and eigenfunctions are sin n pi x, m pi y. So, therefore, the eigenvalues are beta m is equal to m pi, where index m runs from 1 to up to infinity, and eigenfunctions are y m is equal to C2 sin m pi y. And now let us look into how the lambda varies. So, this is the definition of lambda. So, lambda m n square is equal to nothing but alpha n square plus beta m square. So, this will be m square plus n square into pi square, and we can get the time varying part now. T m n dt m n dt will be is equal to minus lambda m n square, and after integration we will be getting T m n is equal to, let us say, C3 exponential minus lambda m n square times t. So, this gives the solution of the time varying part. Now, we are in a position to construct the complete solution of u. Now, if you really look into that, then u as a function of x, y, t now becomes, there will be 2 summation 1 over m 1 to infinity, another over n 1 to infinity, C1, C2, C3, 3 constants, they will be multiplied. So, they will be giving rise to a new constant Cmn exponential minus lambda mn square times t. Okay. So, here if you write down that this is correct, but alpha n is 2n minus 1 pi by 2. So, therefore, lambda mn square will be 2n minus 1 square pi square by 4 plus m square pi square. So, if you take pi square common, so this becomes 2n minus 1 square of that by 4 plus m square pi square. In the previous case, when we have the differential boundary condition on both x and y direction, we had lambda m n square as m square plus n square into pi square. But in this case, one of the eigenvalue is 2n minus 1 pi by 2, another eigenvalue is m pi. So, therefore, the expression of lambda m n square will be 2n minus 1 square by 4 plus m square into pi square. Okay. So, Cmn exponential minus lambda m n square t sin cosine, okay, sin m pi y, and we had cosine alpha n x, where alpha n is nothing but 2n minus 1 pi by 2. Okay. So, again the unknown constant Cmn will be now evaluated from the initial condition at t is equal to 0, u is equal to u naught. So, we had u naught is equal to double summation 1 over m, another over n, Cmn sin m pi y cosine alpha n x. So, we will be utilizing the orthogonal property of the eigenfunction. We will be multiplying both sides by cosine alpha m x and sin n pi y, and integrate over the domain of x and domain of y. So, if you do that and utilizing the separation of variable, then we will be getting u naught is equal to integral sin m pi y dy 0 to 1 cosine alpha n x dx from 0 to 1, and only one term will survive in the right hand side when m is equal to n, and we will be getting Cmn 0 to 1 sin square m pi y dy and 0 to 1 cos square alpha n x dx. We have already seen that this integral is half and this integral is half. So, we will be getting Cmn is equal to 4 u naught, this will be 1 minus cosine m pi divided by m pi, and this will be sin alpha n divided by alpha n. So, I will be getting 4 u naught by m pi, and alpha n is 2n minus 1 pi by 2, and on the numerator we will be having cos m pi sin alpha n. So, this will be 4 u naught over pi square 1 minus cosine m pi sin alpha n divided by m to n minus 1 by 2. So, we will be getting the complete solution. The complete solution will be u x y t as summation over m summation over n c m n exponential minus lambda m n square t sin m pi y cosine alpha n x, where alpha n is 2n minus 1 pi by 2 lambda m n square will be nothing but 2n minus 1 square divided by 4 plus m square multiplied by pi square, and c m n we just evaluated as 4 u naught divided by pi square 1 minus cosine m pi and multiplied by sin alpha n divided by m to n minus 1 pi by 2. So, that gives the complete solution of a 3-dimensional problem, parabolic partial differential equation with a boundary condition, a Neumann boundary condition prevailing at x is equal to 0, and everywhere else all the other 3 boundaries is the homogeneous boundary condition with respect to y and with respect to x equal to 1. So, we will be getting so in the next class. So, I will stop here in this class. In the next class, what I will be doing, I will be taking one step ahead and we will be solving a well posed problem which is 4-dimensional in nature, 1 dimension in time and 3 dimensional in space. Thank you very much.